So let's talk more about use substitution, because as I said last time, and I'll say again, in my opinion, is kind of your go-to method of integration. So I'd say your first thing you want to do if you're trying to anti-differentiate or integrate something is see if you can simplify it. Like, for example, something like this, or something like maybe say the integral of 6x squared plus x plus 4 over x to the 1/4. If I was trying to integrate that, I wouldn't try use substitution first. I would first try simplifying it. And you can either, when you have a quotient like this, where the denominator has a single term, and it would be okay if it was like 2x. In fact, let's make it 2x to the 1/4. That's still a single term because I don't have more than one thing added to it, right? It's just itself. So in this case, you can either rewrite it as 6x squared over 2x to the 1/4 plus x over 2x to the 1/4 plus 4 over 2x to the 1/4. Or if you prefer, you can write it as the integral of 6x squared plus x plus 4 times x to the negative 1/4. You still have division by 2 dx. Either way is fine. I happen to be more of a fan of this first way of doing it. Either way should get you to the same place, though. Whichever way you do it should end up with the integral. Let's see, 6x squared divided by 2x to the 1/4. Well, 6 divided by 2 is 3. And x squared divided by x to the 1/4, we subtract those powers. And 2 minus 1/4 is 8/4 minus 1/4, which is 7/4. Sorry. Welcome, welcome. So we have 3 times x to the 7/4 deal here. The 2 in the denominators have to stick around, so you have a 1/2 as your coefficient. And then x to the first divided by x to the 1/4, we subtract those powers, and 1 minus 1/4 is 3/4. Finally, over here, 4 divided by 2 is 2, and there isn't an x on top, so that x to the 1/4 in the denominator comes up as x to the negative 1/4. I will point out, we just as easily could have said 6x squared times x to the negative 1/4 over 2 is 3x to the 7/4. And x times x to the negative 1/4 over 2 is x to the 3/4 over 2. And 4 times x to the negative 1/4 over 2 is 2 times x to the negative 1/4. So either way you want to go, both ways get you still to the same simplified version. And then after you have simplified, then you have to differentiate. So we're going to add 1 divided by the new power. So we're going to get 3 times x to the, okay, so you want to get to the place where adding these fractions is not too terrible. 7/4 plus 1 is 7/4 plus 4/4. 7 plus 4 is 11. So it's going to be x to the 11/4. And instead of writing divided by 11/4, we're going to multiply by 4/11. It's pretty typical. Same deal here. We have plus 1/2 times, I like to leave a little space. X to the 3/4 plus 4/4 is 7/4. Instead of dividing by 7/4, we're going to multiply by the reciprocal. And then finally, 2 times x to the new power is negative 1/4 plus 4/4, which is positive 3/4. Instead of dividing by 3/4, we multiply by 4/3. In the test situation, I might just leave it like this. In a real life situation, I can't not simplify these coefficients. I would write this as 12/11 x to the 11/4 plus 1/2 times 4/7 is going to be 2/7 because the 4 and the 2 cancel and give me a 2. X to the 7/4, and then 2 times 4/3 is 8/3 x to the 3/4. Let's see. So the first thing you should try to do when you see an integral or an antiderivative is, can I simplify this so it's just powers of x or whatever your variable happens to be? But sometimes that won't be possible. A lot of the time, most of the time, that's not going to be possible. You might have something like, say, the integral of 4x cubed times x to the 4th plus 7 to the 19th power. And although technically possible to multiply out x to the 4th plus 7 to the 19th power, it is not what any of us should do. we should make a u substitution here. There are two big clues as to what our u should be. The first clue is that you've got something inside another function. You've got some stuff raised to the 19th power. That's a good clue that our u should be, I feel like I'm talking about Blue's Clues here. It's a good clue that our u should be x to the 4th plus 7. And the other convincing piece of evidence here is that the derivative of that is also in our integral. The derivative of u with respect to x is 4x cubed, which we exactly have in our integral. I'll point out, it wouldn't matter if we had 4x cubed or 8x cubed or 1000x cubed. The important part is that we have the x cubed. We can always adjust for a constant multiple. Let me give the people on the Zoom here the attendance link while I'm thinking of it. But there's something else I wanted to say, but now I forgot what it was. So there we go. That. Cool. There you go. Those of you in class, fill it out when you have a chance. It's there, and you can grab it later. Something I wanted to say. If that's too hard to grab it, you'll just. Okay, cool. Right. There was, I feel like there was something else. Oh, yeah. I wanted to ask you all, is everyone in Tav's class here? Anyone? No one's okay. So when he does a u substitution, does he like to isolate dx, or does he like is he doing this where he says du equals 4x cubed times dx and then completely saying du divided by 4x cubed equals dx? Does he do that? It's okay if he doesn't. I'm just curious. Right. Sure. Right. So if it were me, it is me, I would stop here and then start you don't have to. I kind of like to rearrange things so that the right pieces are next to each other. You can totally just say, oh, look, I've got 4x cubed times dx. So that's gonna be equal to my du. But if you prefer to make it easier to see, you can rewrite this, right? Order of multiplication doesn't matter. You can totally write this as x to the 4th plus 7 to the 19th power times 4x cubed dx. And then it's even easier to be like, oh yeah, this 4x cubed dx is equal to du. I will emphasize, I think you should always make sure that the dx piece is transformed into the du piece before you do anything else. There's a really good reason for this, which we'll see in a little bit here. Because there are some examples where you can kind of miss it if you're not paying attention. And then here, the insides there are going to be what u is. So I'm going to rewrite this integral in terms of the language of u. It's going to be u to the 19th power times du. And now we have something that we know how to anti-differentiate. We use the anti-power rule. We get u to the 20th divided by 20 plus c. Hey, Megan, come on in. And then we plug back in what u is equal to, because for indefinite integrals, aka antiderivatives, you have to end with the same variable you started with. We started with x's, we need to end with x's. So we're going to have a x to the 4th plus 7 to the 20th power divided by 20 plus c. That is our answer. Nikki, you look like you have a question. It's okay if you don't. You just, I feel like your face is like, I have something to say.
When this was like divided by also like something, for example, like that, you would also split it up?
So maybe. Here's the real kind of broader answer. Integration is hard because it's not always clear what you should do. Sometimes it's a u sub. Sometimes it's integration by parts. Sometimes it's simplifying it first. Sometimes it's another method we haven't talked about yet. There's probably like 3 or 4 methods of integration that we talk about in this class, and it's not always super clear what's to be done first. We have some kind of guardrails that help us decide what we should do first. And so when I'm thinking about, so again, and here's the kind of process in order. The first thing you should do is, can I simplify this so it's something like this, or so it's something like our first example here, where we said, oh yeah, just divide everything by the denominator there. But if you can't simplify it, or it doesn't seem like it's simplifiable, then usually my next method that I think about using is, can I do a u substitution? Is there a good choice for u? And again, I'm going to look for those two things. Is there something stuck inside another function? And is there something whose derivative is equal to another piece in the integral? We hope to get both of those. We'll settle for one of them. Sometimes we'll settle for none of them and still use U substitution. So let's look at another example. Let's say we're going to have the integral of x to the 6th times the square root of x to the 7th plus 9. And just like before, I would say we have both things we want to be true being true for a U sub, right? I should actually say we can't simplify this, right? There's no simplifying here that can be done. We are stuck with what we've got. It doesn't get any nicer. But I can certainly think of letting U equal the stuff that's stuck inside the square root. That's going to be x to the 7th plus 9. And then the derivative of that. Now, most people skip what I'm about to write. Instead of writing du dx equal to the derivative, which is 7x to the 6th, most people skip that step and jump straight to writing it as du equal to 7x to the 6th times dx, which is totally fine. Just remember where it's coming from, right? It's really coming from the fact that you're just finding the derivative, then you're moving the differential dx over to the other side. Now, here's where I don't know what you would prefer to do. I would prefer to do this. I would prefer to say, well, look, my integral almost has what I want. I'm going to rewrite it so the stuff that I want to be next to each other is next to each other, although you don't really need to do that. And then I would like to say, oh, well, look, I have that over here. It's right there. So just divide both sides by 7. So the du divided by 7, or 1/7 times du, is equal to x to the 6th dx. That's what I would choose to do. And so then I get to say that this part of my integral is equal to 1/7 times du. Now that I've taken care of dx turning into du, which is always the thing we should do first, then I'm going to replace everything else with what I can. That's going to be u. Other people might say I would rather write dx equal to du divided by 7x to the 6th, and then take this integral here and rewrite it as the integral of x to the 6th times the square root of x to the 7th plus 9 times dx replaced by the du over 7x to the 6th. And then they cancel the x to the 6th. This is not the way I like to do it, but it does work just fine. And so then after I deal with that, I plug in what's left. So I still have this x to the 7th plus 9 here, which is u. So I'm going to rewrite that as the integral of the square root of u times du over 7. Or more normally, I'd bring out the 1/7 and have the square root of u du. I mean, it's really the same work, right? I just like viewing it as I'm going to replace this with that. So I'm going to write this as the square root of u times 1/7 du. Those are the same thing. That and that are the same. Whichever way you want to view it, totally fine with me. Again, I don't like doing it this way just because I don't. But not for any good reason, just because I learned how to do it one way and that's the way I've always done. I would do two things here. I would always choose to bring a constant multiple out in front of an integral. And then, of course, I don't want to leave this as square root of u. I want to write it as u to the 1/2 power so that it's easier to apply the anti-power rule to. So then we do the usual thing. We get 1/7 times, leave myself a little space. U to the 1/2 plus 1 is 1/2 plus 2/2, which is 3/2. And we don't divide by 3. Well, we do. We divide by 3/2, but we rewrite it as multiplying by 2/3. Slap on a C, and then change back to the variable we started with. 1/7 times 2/3 is 2 over 21. U is equal to x to the 7th plus 9. So it's x to the 7th plus 9 to the 3/2 power plus C. And that is our antiderivative or indefinite integral of x to the 6th times the square root of x to the 7th plus 9. A lot of the times, I don't know. A lot of the times it feels like, in my opinion, they try to make the U relatively obvious. But that also could be through the lens of experience, right? I've been doing this for a long time. So a lot of times I'm like, oh yeah, well, clearly U is that, where it might not be so clear to everyone else. So we'll try not to be so biased in my opinion of what is obvious and what is not. But let's look at this example. The integral of x plus 5 over x squared plus 10x plus 7 to the third power. That 10 looks not the best. All right. What do you all think a good choice for you might be? Right, the x squared plus 10x plus 7. Right, so go ahead, let u equal that, find du, and then see if you have it. Yeah. All right, let's see what we've got. So u is, or we think, again, integration is a guessing game. You are guessing what you think the right thing to do is. And as you get more experience, your guesses become more educated. But still, some of the time, like the other day, I was helping someone to drop it, and I was like, I don't know, let's try this. And it didn't work. So then we tried something else. So sometimes you're going to guess the wrong thing, and that's totally fine. You stop when it looks terrible and you try again. So then du here is going to be 2x plus 10 times dx. Now, do I exactly have that? No, but I have a multiple of that. So you can either go one of two ways. Some people, me probably, would divide both sides by 2 here and say, or multiply both sides by 1/2. 1/2 times du equals 1/2 times 2x plus 10 dx, which is x plus 5 dx. Some other people would actually multiply by 2 up here and say times 2 and times 1/2 out here to make it work that way. Either way is fine. So then we start rewriting. This is going to be equal to, so there's my 1/2 du. So I'm going to have 1/2 du on top over u cubed. I'll point out just for some clarification, I would bring out the 1/2. And sometimes people do write du over u cubed, which I find annoying. I don't love that notation personally. I would probably choose to write it as, well, I mean, honestly, I wouldn't write it like this, even though I'm going to. I like this better though, right? That du over u cubed is the same as 1 over u cubed times du. But really, I should write it in a way that's easy to integrate. I should write it as u to the -3 times du. And then we use the anti-power rule. Most of the time, not all the time, a lot of the time, when you're doing a u sub, you eventually get to a place where you have u to a power, and you just use the anti-power rule. Not every time, but a lot of the time. So we're going to get u, oh, sorry, don't forget the 1/2 out in front. We're going to get u to the -3 plus 1 over -3 plus 1. And this is, if sure, u to the -2 over -4 plus c. And then I'm going to plug back in what u is equal to and get x squared plus 10x plus 7 to the -2 divided by, I probably wouldn't write divided by -4. Usually if you have a negative in your denominator, you put the negative part out in front. Write it as just negative that over 4 plus c.
Could you do the 1 over n plus 1, I mean n minus 1 u to n minus 1? Or no?
1 over n minus, no. What do you mean exactly? Like it's fine.
Instead of, how you
Like from here?
Yeah, isn't there a rule that you do like 1/n-1 x and to the power of n-1?
Maybe. I would never think of it that way. Let's see. Does it work here? So you're basically saying I could say that 1 over u to the n, the integral is, what is it again? Say it again. 1 over,
and then
u to the, no. It's almost the same, except you're missing a minus sign. But here's what I really want to say. And not to discount this, but why would I spend my mental energy trying to memorize another rule when I don't need to? Really, honestly, I want to memorize as few things as I have to. I don't want to try to remember a different version of the anti-power rule. So I would really, really strongly say, don't try to do that, because I'm going to mess it up. I'm not going to get it right. I'm going to miss a minus sign. Rewrite your 1 over u to a power as u to the negative power, and then use the anti-power rule. That is almost always what we should do. So then this is u to the negative third, we add 1, divide by the new power, and then we get this. I would probably rewrite this final answer as negative 1 over 4 times x squared plus 10x plus 7 to the positive 2 plus c, just because I am biased towards positive powers. But either answer is totally correct and fine. Couple more examples, though. I mean, always a couple more examples. A couple more examples, and then a couple more examples, and then a couple more. Let's look at this next example, because this next example actually illustrates something that I think is really important. Which, I mean, is probably true about most examples I talk about, because I'm always trying to show you something. So we want to try to find the integral of e to the square root of x over the square root of x. And yeah, I'm going to try to keep the numbering going here. This is number 4. Did I write down number 2 before? Probably not. Let's see. Oh, I did. I could get them. All right. So seems like there's a good choice for you. U could be the square root of x. It's stuck in the exponent. It's also stuck in the denominator. And the denominator is definitely a place you can be stuck in. So I think u equal to the square root of x is a great choice, which I might think of as u equal to x to the 1/2. So that it's easier to find the derivative. My derivative, actually my du is going to be my derivative, which is 1/2 x to the negative 1/2 times dx. And then I would choose to rewrite this as du equal to 1 over 2 times x to the positive 1/2, or 2 times the square root of x dx, because I feel like it makes it easier to see that that's similar to that. And I would then say, well, I have a dx over root x, so I would really like to multiply both sides by 2 and say that 2 times du equals 1 over root x times dx. And now here's why I want to emphasize the fact that we really, really, really need to make sure that we take care of the du dx changeover before anything else. If we just start willy-nilly replacing things with things that look like u with u, you might say, oh, this is going to be the integral of e to the u over u. Because those are technically both u's. And then you'd have a dx, and you would not be happy about that. That's a problem, right? I don't want u's and x's together. So here's the deal. We have to make sure that we take care of this first. So I'm going to think about this integral really as the integral of e to the square root of x times 1 over square root of x times dx. And then this 1 over root x is going to get taken care of by being equal to 2 times du. And then the remaining square root of x, that gets to be replaced by u. So we're going to rewrite this as something that's easier to integrate, by the way. The integral of e to the u times 2 du. Again, I would bring out the 2, even though you probably don't need to write that step, because integrating e to the u is kind of the easiest antiderivative ever. The antiderivative of e to the u is e to the u. So we get 2 times e to the u plus c. You don't need to multiply the 2 by the c, because 2 times a constant is still a constant. So any constants that are out there, just write plus c. And then I see the chat, I'll look at it in a second. And then we replace u with what it's equal to. So we get 2e to the square root of x plus c. Let's see what's in the chat here. Why wouldn't the x multiplied? Okay, all right, cool. I'm glad you answered your own question. Other questions about this? Here's a similar type of example, but not quite the same. Let's look at, let's look at this. Let's look at number 5, the integral of e to the 6x over the square root of e to the 6x plus 2. I know I didn't really say it last time, but I should have said it. The reason that the square root of x was also a good choice was, in addition to being stuck inside some other function, its derivative, 1 over 2 root x, again, not worrying about the constant 2 there, is essentially in the integral. We have a 1 over root x. That's great news. That always means we're probably making the right choice. Probably. There are no absolutes, except for absolute values. So you should be what here? What do you all think you should be here? Plus 2. Yeah. The stuff inside the root there. And most of the time, if you're debating whether or not to carry, like to also include the plus 2 or the plus 5 or the plus whatever in your choice of u, you almost always should, because the derivative of it is not going to make any difference, right? The adding the constant isn't going to change your derivative at all. So let's see what du is here. Du is going to be the derivative of e to the 6x is e to the 6x times 6. And then dx. Oh, look, I have that. Well, I essentially have that, right? I need to divide both sides by 6. So 1/6 du is equal to e to the 6x dx. So then the part I just circled in red there, that's equal to my 1/6 dx. So this ends up being the integral of, oh, I said the wrong thing there. I said 1/6 dx. I should have said 1/6 du. So we have a 1/6 du on top and a square root of u on the bottom. All right, finish that integral. Rewrite it a little bit. I'll start rewriting it really slowly, but you should already be ahead of me. All right, so I don't think you need, like, I think you could have jumped straight from there to there. You don't need to write these 3 different things here. 1/6 over the square root of u is the same as 1/6 times u to the negative 1/2. But we still have to integrate it. So we integrate, and the antiderivative of u to the 1/2 is u to the negative 1/2 plus 1 divided by negative 1/2 plus 1. Oh, I probably could have skipped writing divided by 1/2 there. Instead, have written 1/6 times 2 times u to the 1/2 plus c, which is going to be 1/3 times the square root of u, which is the square root of e to the 6x plus 2. Style preference, I like writing a square root of my stuff versus my stuff to the raised to the 1/2, but it's just as correct to write it as 1/3 times e to the 6x plus 2 to the 1/2 power. See. Either way is fine. I just like writing a square root. Let's see here. No. Oh yeah. Yeah, let's do. Interesting. Let's not do that. Okay. Let's talk about some logarithms. Some log integrals. So the integral of 1 over x dx is equal to the natural log of the absolute value of x. I do want to stress, you usually need the absolute value there. In fact, I should say, it is never wrong to write the absolute value there if you're integrating 1 over x and getting the natural log of x, natural log of absolute value of x. That's later. That's later, James. Yeah, but oh yeah, we'll just yeah. Sorry. So I've got some examples I just want to point out. So and the integral of 1 over u in the same sort of way is the natural log of the absolute value of u. So there's lots of things we could do. For example, if I was going to integrate 1 over x plus 4, I could do a u sub here. There's really only one plausible choice for u. The stuff stuck inside the denominator, right? There's nothing else even to pick. By the way, whenever you're doing u substitution, choosing u equal to x is never a good choice because all you're doing is rewriting the integral with a different letter, right? If I, for example, if I was trying to do the integral of x e to the x squared, and I somehow decided I wanted to let u equal x, and then du is 1 times dx, all that happens is this becomes the integral of, well, that becomes du, x becomes u, x squared becomes u squared, and it's the same integral, just written with a different letter. So with a u sub, but I want you to listen to the words I'm saying. When it's a u substitution, we never ever choose u equal to x or whatever your variable happens to be. But when we talk about integration by parts, it is totally fine to let u equal x. So we'll get there when we get there, but I just want to let you know. All right, so back over here. I guess. So I would let u equal x plus 4. The derivative of x plus 4 is 1 times dx. Whenever you let u equal x plus something or x minus something, your du is just going to be dx. So the transformation is easy. This becomes, well, dx becomes du, and 1 over x plus 4 is 1 over u. So we're going to get the natural log of the absolute value of u, which plus c, which is the natural log of the absolute value of x plus 4, plus c. But I feel like we could have done that without actually having done the u substitution. I think we could probably see, oh, and I was going to write some numbers here. Sure. The integral of like 1 over x plus 7. I think it's a pretty straight shot to say, yeah, that's the natural log of the absolute value of x plus 7 plus c. No u sub required. In fact, I think we could even go a step further and say the integral of 1 over maybe 3x plus 4. Well, I'm pretty sure it's going to be the natural log of 3x plus 4. Almost. Here's the check. And I would say when you do this part in your head, ignore the absolute values for a second. Meaning, well, here's what I'm about to ask you. What's the derivative of the natural log of 3x plus 4? What? 3 times. You're saying the m part. There's a middle part though. So, right, what's the derivative of the natural log of some stuff? It's, and then we multiply by, yeah, exactly. But look, in here, I don't have the times 3. right? The derivative of this should be that. But for the derivative of this to actually be that, I need a division by 3 out here to counteract the eventual multiplication by 3. This is the same pattern I was talking about on Tuesday. Then when your derivative would make you multiply by a constant, your antiderivative is going to make you divide by that same constant. Or you could do it the long way. You could say, we're going to let u equal 3x plus 4. du is going to be 3 times dx. 1/3 du is going to equal dx. And then you take this whole integral and you write it as the integral of 1 over u times 1/3 du. You bring the 1/3 out in front because you can't help yourself. And then you integrate 1 over u, and you get the natural log of the absolute value of u, which then becomes 1/3 times the natural log of the absolute value of 3x plus 4. Oh, look, it's the same answer. I don't think you need to do all this work to get that answer. You're welcome to, and it's totally fine to do it, especially the first few times you're doing this to see what's happening. But eventually, I'm just going to say that if your choice for u is a linear function of x, mx plus b, 3x plus 4, 2x plus 7, negative 3x plus 5, you can almost always get away with just dividing by the coefficient of x and then doing whatever the normal process would be. In fact, yeah, I think that's a good place to do that. I got a handout for you. Veronica, right? No, Victoria. I was thinking the name is always Megan. Cassie. Yeah. I've known many Veronicas and Victorias in my life, and it's Rebecca and Rachel too. Her names are just like, for some reason I will know your name and then like it's just like I can't get it. Like I always say the wrong one. Victoria. So looking at this handout here, I want you to see the same kind of idea works for all these things. So if we're going to integrate 1 over x plus 5, it's going to be equal to the natural log of the absolute value of x plus 5 plus c. Integrating 1 over 2x minus 3, the same idea happens. It's going to be the natural log of the absolute value of 2x minus 3 plus c, except what do I need to divide by? Show me on your fingers. There you know. That many, yes. We need to divide by 2. I'm going to say times 1/2, but we have to divide by 2. So that when we take the derivative of this, the derivative of 1/2 times the natural log of 2x minus 3 is 1/2 times 1 over 2x minus 3 times 2. And the 1/2 and the 2 cancel each other out. Let's look over here to the right. The antiderivative of e to the 3x is going to be e to the 3x divided by 3, or times 1/3. Why don't you all fill in the next box here? The integral of e to the negative 2x. We could do a u substitution here, but I don't think we need to. So if the derivative would make us multiply by 3, the antiderivative makes us divide by 3. The derivative would make us multiply by negative 2. The antiderivative makes us divide by negative 2. Same thing is true here. What's the antiderivative of sine of x? Was it positive or negative? That's the derivative. Negative. The antiderivative of sine of x is negative cosine of x. So the antiderivative of sine of 3x is negative cosine of 3x. What do we need to divide by? Right, or multiply by 1/3. You can write it either way. You can write it as negative 1/3 cosine of 3x. you can write it as negative cosine of 3x divided by 3. Either way is fine. Same deal here. If I'm anti-differentiating sine of negative 2x, I get negative cosine of negative 2x. But then I'm going to divide by negative 2. Or I'm going to write it as negative 1/2 cosine of negative 2x. I would normally simplify that as positive 1/2, but I really want to explicitly view that we have negative cosine divided by negative 2, or negative cosine times negative. What's the antiderivative of cosine of x? Yeah, positive sign. So the antiderivative of cosine of x is sine of x. The antiderivative of cosine of 4x is going to be sine of 4x divided by, right? Or if you prefer, 1/4 sine of 4x. Same deal here. The antiderivative of cosine of something times x is going to be sine of whatever you have times x divided by whatever is multiplying x. Which seems kind of terrible to write. I would probably choose to write this as 2 times sine of 1/2. Let's see. And we can keep going. So right over here, the integral of 1 over 6 minus 3x is going to be the natural log of the absolute value of 6 minus 3x divided by negative 3, or multiplied by 1 over negative 3. Or really negative 1/3, I shouldn't have said, but it's trying to be more. And we can even go very general, right? If you have 1 over a linear function of x, some ax plus b or mx plus b or whatever you want to call it, it's going to be the natural log of the absolute value of ax plus b, but then I have to divide by the coefficient of x. Because again, the derivative of the natural log of some stuff is going to be 1 over the stuff times the derivative of the inside stuff. And the derivative of a times x plus b is a times 1 plus 0. Or in other words, we multiply by a. We have to cancel it out. Should we fill in the rest of the chart, or do you guys feel like you got it? Now let's fill it in. Because some of these are a little bit funky, right? This is really the integral of e to the 1/8 times x. So the antiderivative is going to be e to the 1/8 times x, or x over 8, divided by 1/8, the coefficient of x. And I would certainly rewrite that as 8 times e to the x over 8. Let's see. Same deal here. For the antiderivative of e to the ax, it's going to be e to the ax divided by a, or 1 over a times e to the ax. So as you might have gotten the kind of, as you might see, I think it's really important that you're able to do this easily. I really, I mean, again, you are welcome to do whatever you want. And if you want practice doing it the longer U substitution way, you should take that practice. But we want to be able to do these fast so that we can focus on doing the other harder parts of integration, which are going to come up. So, right, we don't want to do u equals x over 4 here. We want to say, oh yeah, this is sine of 1/4 times x. We're going to get negative cosine of x over 4 divided by the coefficient of x, which is the same as negative 4 times cosine of x over 4. And same deal down here. The antiderivative of sine of something times x is going to be negative cosine of that same stuff divided by the coefficient of x, or negative 1 over a times cosine of ax. So I'll say it one more time and then we'll stop. If you have a multiple of x, it can't be something else. It can't be like x squared or x cubed or anything more complicated than just a multiple of x plus a constant. If that's your situation where that's like would have been your choice for u, then we get to just divide by the coefficient of x. So the antiderivative here is going to be sine of negative 3x divided by negative 3. Right? Using the normal rule, like when I look at that, I'm thinking, oh, I've got cosine of some stuff. And the antiderivative cosine is sine of the stuff, but then dividing by the constant multiple of x. And finally here, this would be sine of ax divided by a. So let's see, let's keep things in order here. That said, we have to be careful with logarithms. For example, if someone said, what's the antiderivative of 1 over, x plus 2, we can easily be like, okay, well, that's going to be, I don't know why with the integral symbol again. I don't need that. I'm going to just do it. That's going to be the natural log of the opposite value of x plus 2 plus c. But if someone said something like, find the integral of 1 over x squared minus 1, and we don't know how to do this yet, but we will learn it eventually, that's not equal to the natural log of the absolute value of x squared minus 1. How do I know? Because I know how to take derivatives. The derivative of the natural log of the absolute value of x squared minus 1 plus c, well, the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is equal to 2x over x squared minus 1, which is not the same as my integrand. So the antiderivative of this is not that, because the derivative of that is not that. And again, we don't have the tools yet to find this antiderivative. So you'll just have to live with not knowing what it is for a while until we talk about partial fractions. But you might have an integral like, say, yeah, let's leave that one. The integral of 2x over x squared plus 9. And then I see a pretty good choice for u. U is x squared plus 9. Because, well, 1, its derivative is there. It's 2x. I've exactly got that. So I can totally rewrite this as, there's my du. There's my u. I can rewrite my integral as the integral of du over u. And a lot of people will write it that way. It's certainly fine. I like to rewrite it as 1 over u du in my integral, just because I feel like for me, it's just easier to see what's happening there.
Then would you be like, oh, like this is the natural log of that?
Yes, for sure. Yeah. So the antiderivative of 1 over u is for sure the natural log of the absolute value of u, which is going to be the natural log of the absolute value of x squared plus 9 plus c. I will point out this answer here, you technically could get away with dropping the absolute values, because x squared plus 9 is already always positive. So taking the absolute value of it is an unnecessary step. So in a textbook, you would probably see someone write the answer as the natural log of parentheses x squared plus 9 plus c. You don't have to do that. It is also perfectly legit to just leave the absolute values there and be safe. And that's what I would choose to do. But I just want you to know that if you're trying to look and answer in the back of the book and you see this instead of that, the reason that they've done that is because the thing inside the absolute value already was always positive. So they didn't need to write those absolute values. The thing I really want to stress is that just because you have 1 over something doesn't mean the antiderivative is the natural log of that something. It's only really true if your something is a linear function of your variable. 1 over u to the first, 1 over x to the first plus 2. Right? If you have other powers, everything goes out the window. So for example, one more example here, yeah. If I was trying to find the antiderivative, say like 1 over 4x plus 1 squared, it's not going to be the natural log of 4x plus 1 squared plus c. I didn't write the absolute values here because I didn't want to, and I don't need to because it's not the right answer. And also 4x plus 1 squared is always positive. But right, again, for the same sort of reason, if you take the derivative here, the derivative of the natural log of some stuff is going to be 1 over that stuff times the derivative of the inside stuff, and the derivative of 4x plus 1 squared is 2 times 4x plus 1 to the first times 4. And if you simplify, you end up getting 2 times 4 over 4x plus 1. And that is definitely not the thing that we started off integrating. So again, I'm going to state, if you've got 1 over mx plus b, you can totally use logarithm. The antiderivative is the log of what you've got. Or 1 over u, the antiderivative is the natural log of the absolute value of u. But if you have something with powers other than 1, essentially, in your denominator, it's probably not going to be a natural log, or at least not without doing some u substitution type work. Here, what do we do instead? Well, here I would do a u sub. So the only plausible choice for you is what? All our whispers. Yeah. U is 4x plus 1. I am going to say actually, well, after we do it, I'll say something. So u is 4x plus 1. Hey, look, I'm making a choice for u that u is equal to just a linear function of x. I could probably skip it, but I'm not going to this time. My du is 4 times dx. I don't have a 4 up there, so I'm going to say 1/4 du is equal to dx. And then I'm going to rewrite my integral as the integral of I almost broke my own rules here. Don't do 1 over u squared first. Deal with dx first. So the dx part is going to be the 1/4 du. And now that I've dealt with that, then deal with that. I know it's not really a big deal, but it's good to be consistent. I would choose to rewrite this as 1/4 times the integral of u to the -2nd. Then I can just use my anti-power rule and get 1/4. Trying to make my 4's not look like u's. 1/4 times u to the -1 divided by -1 plus c. I would rewrite this as -1/4 times 1 over u plus c, and then finally replace what u with what it's equal to, which is 4x plus 1. I guess you could write that as -1 over 4 times 4x plus 1. Let's see. But what I really want to say here is that I'm actually kind of thinking of this as just the integral of 4x plus 1 to the -2nd. And if I use the anti-power rule, I'm going to get 4x plus 1 to the -1 divided by -1. What else do I need to divide by? I would say multiply by 1/4 or divide by 4. Right, I need a times 1/4 because of the 4 that's a multiple of x there. So again, I see that if my choice for u is just a linear function of x, some mx plus b, you can kind of just apply the normal rule. You're like, oh, I've got something raised to the -2nd. Use the anti-power rule, get that something to the -1st divided by -1, and then divide by the coefficient of x. And that, although it doesn't look exactly the same, that is the same as this. Right, my 4x plus 1 is in the bottom, it's 4x plus 1 to the first, or 4 in the bottom, or 4x plus 1 to the -1st on top. And then you've got a -1/4, and you've got a -1/4. Those are the same answers. I've just written them slightly differently.
So the reason that we can't like do, cause like I was kind of thinking like after the step where it's like 1/4 the integral of 1 over u squared times u. Like I was thinking like 1/4 times the natural log, no?
Nope.
Because
But
of the square?
because of the square, because of the same reason that, no, where'd you go? Well, like, I mean, literally because of what we have up here, right? Because when you have, if you said that the natural log of whatever squared, then the derivative of the natural log of something squared doesn't end up working out to be the derivative you want it to be. So yeah, really, I will say the only time your integral ends up being a natural log is if you're integrating 1 over a linear function of your variable. So 1 over 3x plus 2, 1 over 5u plus 1, those would all give you logarithms. But once you start getting other powers in your denominator, logs are out the window. Yeah. Oh yeah, we should look at that. We still need to talk about so many things, so many things. Let me do 2 more examples, then we should start talking about fundamentals in calculus, because yeah, we've got how much time? So got like 25 minutes. Yeah. Let me give you 2 more examples. So let's say we have the integral of x plus 4 over sure x squared plus 8x plus 1 dx. I don't know what to do, so I'm going to try a u sub, and the choice we would usually pick, you'd usually pick u to be the thing in the bottom. For, again, the usual reasons. It's stuck, and also, more importantly, its derivative looks like it might work out. It's not exactly what I have on the top, but it is exactly a multiple of what I have on top. I'm going to do this one slightly different than I did the other one. Instead of dividing both sides by 2 here, I'm going to show you the way other people sometimes approach this. I'm going to rewrite this integral as the same integral. I'm going to write some parentheses there, and you'll see why in a second. And then I'm going to multiply that integral by 1. Same thing, right? I didn't change a thing. It's still the same integral. I just I multiplied by a 2 and by a 1/2. But now you can see that the numerator is exactly 2x plus 8 dx on the end there. And the denominator is my u. So I can definitely rewrite this as 1/2 the integral of 2x plus 8 dx is my du. And the denominator is just my u. And now that it's du over u to the first, we can say that it's going to be natural log of the absolute value of u as our antiderivative. Let's see. And then we plug back in what u is equal to. We get 1/2 natural log of the absolute value of x squared plus 8x plus 1. Let's see. And I'm not even going to begin to think about whether or not the inside of that is always positive or not. I don't care. I'm going to leave the absolute values and not spend mental energy that I don't have time to spend. It might always be positive. It might not be. I don't know. You can find the discriminant and see if it's positive or negative, right? There's lots of work you could do, but none of it is necessary. Okay, but what if we do the flip now? Do I have enough room here? Yeah, I should get this piece of paper. Okay, so all that wasted space gone forever. So what if we do the integral of x squared plus 8x plus 1 over x plus 4? Letting u equal x plus 4 is not going to help. Letting u equal x squared plus 8x plus 1 is not going to help. And here's why. If you were to let u equal x squared plus 8x plus 1, your du is 2x plus 8 dx, which is 2 times x plus 4 times dx. And I want to be extra clear here. We don't have x plus 4 times dx in our integral. We have 1 over x plus 4 times dx, and that is completely different. So this u sub is not going to help us. No good. Typically, when you have a rational expression like this, where it's a polynomial divided by another polynomial, and the degree on top is greater than or equal to the degree on the bottom, we do polynomial division. So the degree of x squared plus 8x plus 1 is equal to 2, which is bigger than or equal to 1, which is equal to the degree of x plus 4. That means we're going to do polynomial division. If you remember in synthetic division, I guess you're welcome to do that. I would not ever. I remember it for a while, but no. Synthetic division, if you don't know what I'm talking about, good. Don't bother. Just do it the regular long division way. X squared plus 8x plus 1 divided by x plus 4. And we ask ourselves, what do you multiply by x to get x squared? And the answer is x. And then x times x is x squared. X times 4 is 4x. You subtract, you can do the thing where you change the signs, that's not my jam. X squared minus x squared is 0. 8x minus 4x is 4x. Bring down the next thing and repeat the whole cycle. Then you ask yourself, what do you multiply by x to get 4x? And the answer is 4. 4 times x is 4x. 4 times 4 is 16. Subtract. 4x minus 4x is 0. 1 minus 16 is negative 15. Now that the thing here has a lesser degree than the thing we're dividing by, we stop. That's our remainder. And here's what we do. We rewrite our division, x squared plus 8x plus 1 divided by x plus 4 as, I hate this problem. I hate this problem because there's ambiguity in what our answer is. So I want to make, because it's unfortunate that I chose this one. Sorry. That and that are the same. I would really love it if they were not. Oh, well. So your answer is the quotient x plus 4 plus the remainder, negative 15, divided by the divisor, x plus 4. So it's the thing you got, your quotient, plus your remainder over your divisor. And the point of this is that now the thing you were trying to integrate can be written in a way that's much easier to actually anti-differentiate. So the integral of x squared plus 8x plus 1 over x plus 4 dx is equal to the integral of x plus 4 minus 15 over x plus 4. And then the antiderivative of x is x squared over 2. The antiderivative of 4 is 4x. The antiderivative of 15 over x plus 4 is the same as the antiderivative of 15 times 1 over x plus 4. And the antiderivative of 1 over x plus 4 is the natural log of the absolute value of x plus 4. Let's see. So when your degree on top is greater than or equal to the degree on the bottom, polynomial division is almost always the way to go. Yes. Let me show you one more, just so we can see one more. One more that's actually kind of funky. So we have the integral of x plus 3 over x minus 1. The degree on top is 1. The degree on the bottom is also 1. Some people, when the degrees are the same, like to take a shortcut that I'm not a fan of. I'll show it to you after I do the polynomial division. Let's do the division. X plus 3 divided by x minus 1. Which is a really almost non-step thing to do. But what do you multiply by x to get x? 1. 1 times x is x. 1 times minus 1 is minus 1. Subtract. X minus x is 0. 3 minus minus 1 is 4. So then we can rewrite x plus 3 divided by x minus 1 is the quotient plus the remainder divided by the divisor. Same, right? Same thing as last time, but now it's more clear what's what, right? The quotient plus the remainder divided by the divisor. Sometimes a trick that people like to use when they see that the denominator and the numerator have the same degree is they do this trick where they say, oh, I'm just going to make the top look like the bottom. Meaning, I'm going to say that's going to be x minus 1. But then what do I need to add on so that the top is still the same as it was before? X minus 1 plus what gets me back to x plus 3? Right. Those are the same. And so then they break it up and they say, oh, but that's really x minus 1 over x minus 1 plus 4 over x minus 1, which is really 1 plus 4 over x minus 1. So some people will do it this way when it's easy to do it that way because it feels like less work than doing the polynomial division. Either way is technically fine, but I would I wouldn't do it this way just because I feel like it only really works in very specific situations. But either way, we see that we're integrating this. So we're going to do the integral of 1 plus 4 over x minus 1. And we're going to end up getting x plus 4 times the natural log of the absolute value of x minus 1. Let's see. You should maybe be aware of some things I'm doing that I'm not showing, that we all do without showing. And there's like 3 things, maybe 2 things I did here that I didn't really show. I'm really breaking this up as the integral of 1 plus the integral of 4 over x minus 1. And then I'm actually rewriting that in my head as 4 times the integral of 1 over x minus 1. So people do this addition or subtraction of pieces without actually writing it as addition or subtraction of integrals. They're just like, oh yeah, the integral of that is that, the integral of that is that. I don't need to write it as 2 separate integrals. And maybe a little bit more challengingly, the 4 over x minus 1, we are thinking of as 4 times 1 over x minus 1. So that they're really just doing the integral of 1 over x minus 1, getting the natural log of the absolute value of x minus 1, and then multiplying that result by the 4 that's just hanging up there. You don't need to show any of this work, but you do need to be able to think of it in your head. Okay. We could go on and on and on. Use substitution for days. There's like, I mean, there's lots and lots and lots and lots of examples. But we should spend some of our time, not enough of our time, talking about the fundamental theorem of calculus. So, the fundamental theorem of calculus. I don't love writing out all these words. The fundamental theorem of calculus, or FTC for short. And this is actually, we're going to start with the second part of it because it's the part that's more useful. So part 2. And where'd my example go? I didn't actually print it out. Let me go. Yeah, sure. So let me just say what it is before we actually use it. So the fundamental theorem of calculus part 2 says that the definite integral from a to b of f of x dx is equal to capital F of B minus capital F of A, where capital F of X is an antiderivative of little f of X. Or written more mathily, where the derivative of capital F is equal to little f. Right, those mean the same thing. If the derivative of capital F is little f, that means that capital F is an antiderivative of little f. So what this says is, if you want to find the definite integral from some x equals a to some x equals b of f of x, you find that value by antidifferentiating your function and then plugging in the top limit minus and then plugging in the bottom limit. What this is representative of, so this is how we calculate the net area under f of x that is above the x-axis. Let's look at a nice, straightforward example. Sorry, I keep forgetting that I have this on my phone here. Sorry. Yeah, I like that example. So let's say, yeah, I would like more, always more. So let's say we want to find the area under f of x equal to 2x plus 1 from, yeah, x equals 1 to x equals 3. Here's what this looks like. We can graph y equals 2x plus 1. It's not that bad. Looks something like this. It's got a y-intercept of 1, not that I really care. And then when I plug in x equal to 1, 2 times 1 plus 1 is 3. When I plug in x equal to 3, 2 times 3 plus 1 is 7. So what I'm asking is to find the area under the curve that's above the x-axis. Conveniently, this is a shape that we could break up into shapes that we actually know how to find the area of. I could break this up right here and say, oh, look, there's a rectangle whose base is 2 and whose height is 3. So the area of the rectangle is 2 times 3, which is 6. And I also have a triangle. The area of that triangle, well, the base is also 2. The height is 7 minus 3, which is 4. So the area is going to be 1/2 the base times the height, which is 1/2 times 8, which is 4. So the total area under this curve is 10, just by looking at the geometry of things. And sometimes people will ask you to find the area under a curve, the area under a curve of a shape that we actually can't do using integral calculus, but by just using geometry, like circles, for example. We'll come back around to that, probably not today. But the point here is that the area is 10, but you didn't have to do it this way. We could instead say, I want to find the area under the curve. So the area under f of x equal to 2x plus 1 from x equals 1 to x equals 3 can also be found by doing the definite integral from 1 to 3 of 2x plus 1. So we're still going to start off by anti-differentiating our function, just like we would when we do the integral of a function. So we're going to get the integral of 2x is x squared. The antiderivative of 1 is x. And then we're going to evaluate this from 1 to 3. I would encourage you to say it correctly, meaning we're doing the integral from the lower limit to the upper limit, from the bottom to the top. Try to say it and read it that way. If you get it out of order, it's fine, but it can be confusing sometimes. So now we plug in the top limit first. So we're going to get 3 squared plus 3 minus, we plug in the bottom limit second, 1 squared plus 1. That's going to be 9 plus 3 minus 1 plus 1, which is 10. It's the same number we got doing it the geometric way. So that's great. That means that it seems like this thing actually works, which is good because it should work because it's the fundamental theory of calculus. But it's nice to see an example where we're not just going to believe it and then move on from there. Did your teacher get into the idea of adding up a bunch of rectangles? It's okay if you didn't. I'm just really curious. Does that sound familiar? No, okay. Often, so there is a lot. So kind of like when we did derivatives in 16a, and we talked about the limit definition of the derivative and how you had the limit as h approaches 0 of f of x plus h minus f of x all over h. There's kind of a similar-ish definition for the area under the curve. And the idea really is that you are adding up a bunch of rectangles whose widths get narrower and narrower and narrower. So you're adding up all these rectangles whose heights are the function heights and whose bases are this small change in x. And the way we do that is by doing this. There is kind of a lot of math there that unfortunately we don't typically devote any time to in 16b. Sad about that. But it also is not the worst thing in the world. We certainly, if you all want me to come back to it next week and say like, James, why does this really work? I could talk for a long time about it if you wanted me to. I don't think that's really what you all want though. So I won't do that unless you really want me to, or you can come see me in office hours. I'm happy to talk about it there. But we're just going to move on and say, yeah, the fundamental theorem of calculus works the way it works. So then we might ask questions like, now we're going to stop writing them out, meaning instead of writing out, find, and what time is it? Sorry, I keep looking at 5 minutes. Find the area under f of x equal to 1 over x from x equals 2 to x equals 5. instead of writing all that out, we're just gonna say, find the area under the curve 1 over x from x equals 2 to x equals 5. And we're all gonna be like, oh yeah, that's what that means. The definite integral from 2 to 5 of 1 over x dx means find the area under that curve on that interval. And the way we do it is by anti-differentiating first. So we're going to get the natural log of the absolute value of x evaluated from 2 to 5. Technically, if you really, really wanted to, you could get away with dropping the absolute values here because all of our inputs are already positive, but you don't need to. You can just say that's the natural log of the absolute value of 5 minus the natural log of the absolute value of 2. I will point out neither of these examples we've needed to write plus c. I could have instead written this is going to equal the natural log of the absolute value of x plus c evaluated from 2 to 5. Well, look what happens when I do that. I get the natural log of the absolute value of 5 plus c minus the natural log of the absolute value of 2 plus c. What happens to those c's? C minus c, that's going to be 0. So we never, for definite integrals, write plus c, although you totally could, because they always end up canceling out. So they're totally unnecessary. I will point out that either way you write this, we should simplify this. I don't need those absolute values. It's natural log of 5 minus natural log of 2, because the absolute value of 5 is 5, the absolute value of 2 is 2. And then almost anybody who actually does this is going to simplify this further as the natural log of 5 divided by 2, because we have that rule for logarithms. Do I have time for one more? Let's do one more. So here's one. Yeah, we'll do this one. Find the integral from 0 to 5 of the square root of 25 minus x squared. Someone's going to ask you a question like this, almost undoubtedly. And you might think, let's try u substitution. You're like, well, I don't know how to use sub there. The only good choice is 25 minus x squared, and the derivative is negative 2x, and I don't have an x anywhere outside. And the thing about this is, you're not supposed to integrate it. So this is where your job of knowing what this definite integral means is really important. This definite integral means find the area under y equal to the square root of 25 minus x squared from x equals 0 to x equals 5. What shape does this graph have? It's not a parabola, although you're on the right track. If there wasn't a square root there, for sure be a parabola. Let me help you out. Let's square both sides. So y squared equals 25 minus x squared, and add x squared to both sides. X squared plus y squared equals 25. What kind of equation, or what kind of shape does that equation have? It's a circle. So I'll point out that that's a circle. Y equal to the square root of 25 minus x squared is the top half of the circle. It's a semicircle. So this graph here is really the top half of the circle whose radius is 5. So if I want to find the area under this curve from x equals 0 to x equals 5, it's that area there, which is what fraction of the circle? So the area is going to equal, I wish I'd left myself a little more room here. So that's going to equal 1/4 the area of a circle with radius 5. So 1/4 pi times 5 squared, because that's the area of a circle with radius 5. And you could simplify this as 25 pi over 4. But that's the idea for a problem like this. They want you to be like, oh yeah, I know that means area under a curve. And this particular curve, I can find the area of without being able to do the antiderivative. This function does have an antiderivative. We will not learn what it is in this class. Not that it's beyond durability. It's just not something that's covered in this class. So we're going to not do that. It's fine. But if you see a question like this on an exam, that's what they're trying to get you to do. It's gonna be like, oh yeah, that's a circle. I know the area of a circle, and I can either have a quarter of it or maybe half of it. So if this had been the integral from -5 to 5, the answer would have been 1/2 times pi times 5 squared. All right. All for today. I'll see you all on Tuesday.